Okay. Oh, I just realized I'm not sharing my screen. I just came from another class, so I forget that I have to start everything from scratch. Okay. Can you see my screen?
Yes, I can see it.
Okay. Okay. So we'll go ahead and start this lesson here. I will make the message box available. That way, if you do have any questions at any point during the lesson, you write in your questions, okay? So I'm finishing with the hydrogen bonding. So last week we talked about the intermolecular forces that existed within certain compounds. We talked about the London dispersion force. We talked about dipole-dipole, and now we're about to talk about hydrogen bonding. So with hydrogen bonding, which I wrote right here, start here, with hydrogen bonding, it essentially explains to you how the hydrogen bonding comes to be. So you essentially see hydrogen bonding occurring when you have a hydrogen attached directly or indirectly to an oxygen, hydrogen attached to a nitrogen, hydrogen attached to a fluorine. So we're told here when you have a very electronegative atom that is bonded to a hydrogen, such as oxygen, nitrogen, or fluorine, the electronegative element is strongly pulls the bonding electrons towards itself. So remember from 1411, electronegativity is the ability of the element to pull shared electrons that's supposed to be shared equally to itself. When it does that, it actually de-shields the other elements. So we're told here because hydrogen only has no other electrons, when its electrons are pulled away, the nucleus becomes de-shielded. So it's almost like derobing, de-shielding. We're looking at hydrogen, which before it forms a bond only has one electron. But in a bond, the electron is used to participate in a bond. So when you have another selfish, I call it selfish, element like fluorine forming a bond with hydrogen, but fluorine ends up being very electronegative, and then fluorine draws that shared electrons to itself. The bond is still present, but the behavior of hydrogen and fluorine is such that fluorine ends up with all the shared electrons, so it gets a partial negative sign. Hydrogen ends up with no shared electrons, at least it behaves that way, so it has a partially positive sign. Because the electronegativity is very strong, hydrogen is essentially de-shielded. When this happens, you have now opposites attracting again. The partial negative will attract the partial positive. This specific type of bond is called the hydrogen bond. So it's a type of dipole-dipole interaction, but it's specific for these three types of elements. Okay? So when we see that, to identify this element, you have to draw the Lewis structure. You want to draw the Lewis structure. So number one, I'll tell you first of all, draw Lewis structure. When you draw the Lewis structure, you can tell if you have a hydrogen bond or not. In the Lewis structure, look for either OH bond. The O has to be directly attached to an H, and H bond. The N has to be directly attached to an H, or FH bond. So you're looking for OH, NH, or FH somewhere in your Lewis structure. Okay? And when you have that in the Lewis structure of the formula, that formula can perform hydrogen bonding. So here we're being shown a molecule. It's actually an alcohol, drinking alcohol, ethanol. So we're being shown an organic molecule where you can see the Lewis structure. Actually, everything is not actually spread out, but they made sure to focus on the OH bond right here. When you have the OH bond right here, the presence of the OH bond then facilitates the formation of the hydrogen bond. So the hydrogen bond actually happens between oxygen from one molecule and the hydrogen from the different molecule. So this is called the hydrogen bond. If you have taken biology, the double helix structure in the DNA molecule, you know, the one that looks like coils, that is actually held together by hydrogen bonds. They tend to show hydrogen bonds because they're not real bonds. They tend to show them as dotted lines. Okay, because it's not a real chemical bond. It's more like an electrostatic attraction between oppositely partially charged elements, right? So you see the charge here is partial, is not full. The charge is never full until the bond breaks. As long as the bond still exists, the charge will always be a partial charge. Okay? So they always show the hydrogen bond like dotted lines. So if you go back and look at your biology book, you will see the double helix structure held in place by hydrogen bonds. Okay. So we're told hydrogen bonds are very strong intermolecular attractive forces. They are much stronger than dipole-dipole or dispersion force. So if a substance can form hydrogen bonding, now we're comparing the molecules that are polar to hydrogen bonds and the molecules that are polar to London dispersion force. So remember, the forces we have learned so far, number one, we have London dispersion force. Number two, we have dipole-dipole. Remember, dipole-dipole came from polar compounds, right? And then number three, we have hydrogen bonds. So hydrogen bonds, once again, are technically polar, but polar with a little extra something. And the extra something here is you specifically have hydrogen attached to oxygen or hydrogen to nitrogen, hydrogen to fluorine. One of these, or even a combination of these. Okay? So we are being told here, of the three intermolecular forces we discussed, hydrogen bonding is the strongest. Okay, when you're comparing these three. Now, outside of this category, remember these three forces exist in molecular compounds that are non-metal, non-metal. Once you start bringing in the metals, now we're dealing with metallic compounds and metallic bonds. That's a whole different level of bonding. Okay, so these three we're talking about exist in molecular compounds. Okay, so substances that can form hydrogen bonds usually have a higher boiling point and melting point compared to similar substances that cannot. So it's almost like a privilege for the compound to be able to form hydrogen bonding. And it can do that if it meets one of these criteria, having an HO bond, HN bond, HF bond. Okay, so in this example here, let me go ahead and add to it. We're looking at two formulas. So these formulas here are essentially ethanol versus dimethyl ether. So they gave you the regular molecular formula, C2H6O. Please notice most of the examples here are actually organic molecules, right? Having carbon and hydrogen and oxygen. Okay, so both formulas having different names pretty much have the same general formula. But when it comes to the structure, it's different. So for the first one, the elements are arranged this way. You have CH3, CH2, OH. Okay? So I'm going to draw the Lewis structure of this so you can see. Carbon, carbon, oxygen. These are the central atoms, the three of them. So right here, carbon, carbon, oxygen. The first carbon has 3 hydrogens. So I'm going to draw this like this. This is my shorthand way of kind of going through that quickly. The next hydrogen and the next carbon has 2 hydrogens up and down. Remember, carbon is surrounded by 4 bonds. The last oxygen has got just 1 hydrogen, like that. Remember, oxygen gets to octet by using the 2 lone pairs here and then the bonds right there. So from my Lewis structure, I have to identify, do I see a OH bond? Yeah, I see the OH bond right here. OH bond, there. Because I have an OH bond, this molecule here can perform hydrogen bonding. based on me being able to identify the O directly attached to an H. It's hard to see that when you're looking at this right here. You want to actually draw the structure out, the Lewis structure. So the Lewis structure is very important in this chapter. When you're looking for a hydrogen bond, you have to see the hydrogen attached to the oxygen. It may or may not be attached. The same molecular formula then rearranges itself like this into CH3, O, CH3. Okay? This time my central atoms are carbon, oxygen, carbon, based on the way this is drawn out, right? So I put my carbon here, oxygen, carbon. Okay. The first carbon here is surrounded by 3 hydrogens. So I put 1, 2, 3 bonds. Then I have my oxygen in the middle, oxygen to the right. Then the carbon on the right is surrounded by 3 bonds, 1, 2, 3, right? I have a hydrogen here, a hydrogen here, a hydrogen here. Remember, the central atoms have to be connected to each other. And then on the right, I have a hydrogen here, and a hydrogen here. Then I have my dots on top, dots on bottom. This is the normal bonding pattern we see with oxygen. 2 bonds, they can be apart or together, 2 lone pairs. That's how the carbon achieves oxygen, just in case you're wondering. Okay.
So any
There you are, Jacob. Sorry. Hello.
sorry, I don't know. It took me to a different chat room. I don't know how I did. Oh, so
It disappeared. Yeah, that disappeared. The other one, I don't know what happened. It disappeared. So I had to make a new one. Okay, yeah.
all right. So with 3 molecules, if one of the molecules has a H, is automatically hydrogen, or do you have to do the steps then determine it's hydrogen?
You have to do the steps because we're looking for the connectivity between O and H. O has to be attached to H, or N has to be attached to H, or F has to be attached to H, like that. We're looking for that.
But right here, O attached to C. Is that fine?
So there is no hydrogen bond here.
Yeah, a C attached to the H. I'm sorry.
Yeah, there's no hydrogen bond. Yeah, you see that?
Yeah.
There's no hydrogen bond because the O doesn't attach to the H directly. It has to be a direct attachment. It cannot be indirect. So no hydrogen bonding here.
Okay.
Because this criteria was not met. Yeah, I do apologize about the link. I actually had logged into the original link earlier and I had it on here and I was hanging around talking to my brother. Then I looked up and the link was gone. So to where if you came in later, you couldn't log in. So I couldn't even recreate the link. So I had to create a brand new one. And that's why I sent a reminder. Yeah, sorry about that. I don't know what's going on with Blackboard, but it's been doing that with my other class too. The links I have on there are disappearing, so people cannot log into the same place. If that happens, just, yeah, try to find another link.
It's a conspiracy theory.
Stop. I think it's just the system is getting overwhelmed. But yeah, so with a hydrogen bond, you're looking for an O attached to an H, and you're looking for an N attached to an H, or you're looking for an F attached to an H. You can have a combination of them, but they have to be directly attached. If that criteria is not met, then you cannot have a hydrogen bond. It's kind of like a prerequisite criteria, must happen or else.
So you're saying this is not a hydrogen bond then?
Yeah, there's no hydrogen bonding here at all.
Okay. All right.
So based on that,
it has to meet these 3 criteria in order for that to work. Okay.
Right. Any one of those, yeah. O to H, N to H, or F to H.
Okay.
So because of that, now let's make a judgment. So this top one here can hydrogen bond. Now I mentioned this before, but because we have slept and we have woken up, I want us to go over this again. The way the bonds work are actually incremental. So what I mean by that is a molecule that can hydrogen bond technically also does the other 2 bonding. So what I mean by here is, I'll write here, types of intermolecular force in this molecule here. So let me try to separate this visually, right? In the molecule here, the one that we have here with the alcohol. It has London dispersion force because it's a molecular compound. Molecular meaning they're all nonmetals, right? So these are all non-metal elements, nonmetals. So it can perform London dispersion force. It can also perform dipole-dipole, and it can perform hydrogen bonding. What I'm trying to say is if a molecule can hydrogen bond, it can also do the other two. Okay? Because of that, this has a very high boiling point. Okay? So, what exactly is boiling point? When you're trying to boil, exactly what are you trying to do? You're trying to break the intermolecular force. This molecule has a very high boiling point because you're trying to break through this, break through that, and break through that. You're trying to break through 3 intermolecular forces to change the molecule from one physical state to another. Okay? Another molecule right here that cannot do hydrogen bond are right here, types of force that we see here. Number 1 is present because it's a molecular compound, right? No metal. So these are all nonmetals. And in general, all molecules, all nonmetal molecules have LDF. They all have LDF if they're nonmetal. Number 2, because you have an oxygen and a carbon, you have a heteroatom. So just in case you're wondering the heteroatom, when you look at organic compounds tend to have carbon and hydrogen as the basic backbone. Okay? When we say something is organic in chemistry, we mean it has carbon and hydrogen. If it's carbon and hydrogen only, this usually produces nonpolar compounds. Okay? Number 1. If you have carbon, hydrogen, and the other element, whatever it is, they call them the heteroatoms. And just in case you're writing a list, and make sure you're writing this down. For example, chlorine, sulfur, pick any nonmetal on the right of the periodic table. Chlorine, sulfur, phosphorus, oxygen, nitrogen, fluorine, whatever. Just non-carbon. Then this tends to be polar. Okay? If it's carbon, hydrogen only, tends to be nonpolar compounds. If it's carbon, hydrogen, and any one of these, they tend to be polar. Okay? I know it's a lot of things. 1412 is kind of like a remix of so many things we learned in 1411. And that's the nature of this class. It's like before you even make a conclusion about what has a higher boiling point, you're bringing in like probably 5 or 6 defense items. This is the reason why it's this and da da da. And as you're going through that, you're learning deductive reasoning. Okay? So back to this right here. Because I have carbon, right, the basic backbone of organic molecules, and hydrogen, and the third element, this will have dipole-dipole. But remember, we went through and decided there was no hydrogen bond, so it only has 2 intermolecular forces. So between the two, this has a very high boiling point. This one here is relatively lower. Okay, now I'll go a little faster through the other ones, but I wanted to make sure I made the point here. This will have a higher boiling point because you have more intermolecular forces to break through. This one here is relatively lower because you have only 2 versus the other one having 3. Back to the table. Now we're seeing. Look at the boiling point. Oh my goodness, 78.3. This one here, negative 22. But they have the same elements present. The arrangement makes a difference. Okay? Same thing. Higher melting point, lower melting point. Okay? Can I throw in a mix in here? Yes, I can. Let me try to sweeten the pot or whatever they call that, something about a pot. Why don't we bring in water? Let's bring in water and discuss water. We're about to discuss water, but I want to discuss it in this context. So when you have CH3, CH2, OH, right, with the OH right here, we're told that this one here boils at 78. Was it 78.3 degrees? Yeah, 78.3 degrees Celsius. And then you have water that boils at 100 degrees Celsius. Can you all explain why water boils at 100 degrees Celsius? That's a very high boiling temperature compared to alcohol.
Well, doesn't it have the friction?
The what?
The friction, what's it called? The pressure, the pressure of
Oh, I see what you're doing,
yeah, the
Jacob. We
pressure
go
of
back
the
to the one
atmosphere.
picture we talked about last week. Okay, so we have kind of moved beyond that picture, going from one phase to another. Now we're comparing these two. Oh, snap. We're comparing these two right here, okay? We're comparing these two. So in these two structures, remember, the context here is, you're kind of in the, you're in the neighborhood next to the neighborhood I want you guys to be in. We're just looking at intermolecular force versus boiling temperature. Yeah, that's the context. That's the neighborhood we're in. We're in the neighborhood of how intermolecular forces. Okay, exactly. So the bottom line here is the type of intermolecular force you have. Let me write this down. The type of intermolecular force present, I should say, influences the boiling point temperature. Okay, so we just saw that the more forces, the higher the temperature. So let me make that conclusion also. Number one, the type matters, and then the number matters, right? The greater the number of intermolecular forces, the greater the boiling point. Okay, so that was the conclusion I was trying to get us to in the other example. So type of forces matter. Hydrogen bond is stronger than the other, so it will make the boiling point higher. The number of forces you have matters too. More forces, greater boiling point. So now, even with that, I want you guys, I've already told you what is, like what will happen, but I want you to defend the answer. Why does water have a higher boiling point? What kind of intermolecular forces do each of them have? Let's start with the first one. This one here, alcohol. Can you all list the obvious intermolecular force it has? The one that you can see?
Hydrogen.
Okay. So this one here has hydrogen bond. I'll write it down here. If it has hydrogen bond, what other two intermolecular forces does it also have?
Dipole, and an
Dipole.
intermolecular force.
And then LDF.
LDF, there you go.
Or dispersion, right? They call it dispersion. I just call it LDF, dispersion, right? So the one that has the alcohol has hydrogen bond, dipole, and then dispersion or London dispersion force. Very good. What about water? What does water have?
Has a hydrogen bond, and
Okay.
then
If it has hydrogen bond, what other two does it also have? Okay,
dipole.
dipole, and then London dispersion force, right? If it has hydrogen, it also has the other two. It never has hydrogen without having the other two. Okay? So if it has hydrogen, that means it has all three. Okay, well, so I'm arguing with you now. Well, they both have the same intermolecular force. So you still haven't answered the question. Why does water boil at a higher temperature? There's something more. Look at the structure. Anybody. It's all in the structure. They have the same types of intermolecular forces, right? What does water have that the other one does not have? It's in the
Molar
it's in
mass?
the Lewis. It has what?
More molar mass?
Uh, Actually, I think water is only 18 grams, but I'm glad you went to that. Okay. Water is only 18, but you are in the neighborhood, so I'm happy. Well, I'm not doing the math on the other one, 46. Okay. Water only has 18 grams, the other one has 46 grams. So based on that argument, the other one should win, right? So molar mass is not the reason. But when you're going through, you want to eliminate all the possible reasons. So it can't be molar mass, because if it was molar mass, the alcohol should win. One last thing, they're not more closely bonded. It's not really about the space. Can anybody look? How many OH bonds do you see in water?
Are you talking about one's nonpolar and one's polar?
They're both polar. If they have hydrogen bonds, they're both polar. Dipo means they're polar. How many OH bonds do you see in water? For you to say you had hydrogen bond, you saw an OH bond, right? Bingo, Rocio. There's an OH bond here. There's an OH bond here. Remember how I said the number of bonds matter? I know, right? Isn't this exciting? I'm sorry. This to me, I'm like, man, they got me. That's why chemistry excites me, because I'm always like, I'm going to get them next time. I'm going to look. Yeah, they want you to see that. And so when you look at other organic molecules, when they have a bunch of OHs, then you're like, okay, the more OHs, the higher the boiling point. I mean, once you get what to look at, then you kind of know how to look at this in other molecules, right? So it's not just about having a hydrogen bond. If a molecule has more hydrogen bond, then it justifies why the temperature is higher. So if you get another molecule like ethylene glycol, it has 3 OHs. 3. What do we use ethylene glycol for? Antifreeze, right? Yeah. I was like, why do they just call it antifreeze? Why are they favoring cold temperature? It's technically antifreeze and antiboil. Nobody calls it that because it doesn't sound cool.
It's because they make you go to school so you can learn these fancy words.
Listen, when I'm around my words, my friends, I'm not using these words. It's social suicide. I'm just kidding. No. The number of OHs matter. The kind of bonds matter. If you're looking at molecular versus molecular compound, the type of bond makes a difference in the boiling point. Okay, so this one here, I'm not going to read all the words. What I'm going to do is compare. So they're telling you the boiling points of group 4A versus 6A compounds. So we have a list here. So I'm going to add a page. And I'm not even going to go through the words here. I'm just going to go through the list that we have here. So here they're showing you the graph, okay? And in this graph, somehow these are all, the parts in green, these are all group 6A elements. So there is some kind of group relationship, right? That's the behind the scenes. Usually in chemistry, when we study period and group, the implication is we're setting those together because there's a relationship between the elements because in the same group. Okay, so if I just look at this picture and I judge it, there is a continuous relationship between H2S, H2S, H2SE, and H2TE. But somehow H2O is also in the same group, but it doesn't follow that relationship. This is like your cousin that's acting weird, but it's still a family member because they look like you. but doesn't act like the rest of the family, that's water. So let's see what's going on here. I don't have a periodic table. I should. My husband cleaned my table, and I have no idea where my periodic table is. Let me try to find something here. Okay. So in group 6, essentially what we have is, in the arrangement, we have oxygen, we have sulfur. This is group 6A. We have selenium, and then we have tellurium right here. Okay. So these were then combined with hydrogen to form H2O, combined with hydrogen to form H2S, combined with hydrogen to form H2Se, combined with hydrogen to form H2Te. So what they're trying to show you here is a group relationship. Let me tell you the normal relationship within the group, okay? In the group, the intermolecular force, whatever you're seeing, increases as the molar mass or the mass of the compound increases. So in general, as the mass increases, whatever the intermolecular force you look, because remember we have 3 to pick from: London dispersion, dipole-dipole, or hydrogen bonding. Whatever one you're looking at, it tends to be more intensified, right? More felt when you go down the group. So the general trend is that is our expectation. As you go from top to bottom, the intermolecular force increases. Okay, that's the general expectation, except for when you come to this group 6A, because even though oxygen is part of this group, it behaves differently when it's combined to hydrogen. So back to that graph. If oxygen with hydrogen behave like the rest of the family, we would actually see it somewhere here, and it would be like here, and this would say H2O. So here's my question to you guys. What kind of intermolecular forces do we see between these 3? Okay, to help you out, once again, remember to determine intermolecular forces, draw Lewis structure. I'm just going to draw one and then fill in the other ones. For the first one is H2S. So it's H. H is what? In group 1, and in my formula, so I'm working out H2S, right? I have 2 hydrogens, so I have 2. Sulfur is in group 6, and I only have 1 sulfur, so this is 6. 2 plus 6 is, y'all need to help me with the math. 2 plus 6, 8. Okay, I got that. Okay, eventually. So I got the sulfur in the middle, like the central atom. I have a hydrogen on either side. Single bond, -4. I'm left with 4. Lone pair, lone pair. Y'all, if you need a refresher on Lewis structure drawing from 1411, watch some videos. Yeah, you want to make sure you know Lewis structure, or it will mess you up in this chapter. Okay, so I have the Lewis structure for sulfur, right? I need a space here for sulfur with hydrogen, so I can draw the Lewis structure for the others. That's my sulfur with hydrogen. This is my selenium with hydrogen. This is my tellurium with hydrogen. They're group members, so they're cousins. So they bond the same way. So I have all 3, the bottom 3. Okay. Based on this, since they are all molecular compounds, I can tell you right now, each of these has LDF. Each has LDF. They all have dispersion force, London dispersion force. Okay. What else do they have? Are these molecules?
Dipole and
Okay. They have dipole-dipole. Hold on a second. They have dipole-dipole. All 3 have dipole-dipole. Why do they have dipole-dipole? How can you tell they have dipole-dipole? Because that matters. If a molecule has dipole-dipole, that means you have judged the molecule as polar, right? How could you tell this molecule was polar and this was polar and this was polar? what does it have on the central atom? We discussed this last week. A molecule is polar if the central atom has what?
Lone pairs.
Bingo. You see how many points you're bringing to this just to answer one question? What was the question again? Why is water acting weird? Yeah, you have to bring in all the information. So this is polar because the central atom has lone pairs, right? So that's why LDF works. All molecular compounds have LDF. Because they're polar, they have dipole-dipole. Okay, now, Jacob, we can examine hydrogen bond. What attachments do we have to see to say, yes, the molecule has hydrogen bond? What was it again? O to H, N to H, F to H. Do you see that anywhere in these three molecules?
No.
Exactly. None of these have hydrogen bonding. So when you bring in their cousin water, we know water has hydrogen bonding. We just did a study on that one, right? Comparing with alcohol. So water has hydrogen bonding. We just saw that. LDF and dipole-dipole. So of these three family members, group members, which one has the highest boiling point? Look at the forces I have listed. What do y'all say? Anybody? The greater the intermolecular forces, the boiling point. The more forces you have, how does that influence? The higher the boiling point, right? So while these ones here will technically be lower, water will be higher. Okay, even though these three on the bottom will be related, the water will be higher than the rest of them because the hydrogen bond makes the boiling point extra high, which explains this picture right here, right? That's why water is off the charts. Well, it's still on the chart, but you see what I'm saying? It's so much higher compared to the others. These three here are slowly increasing. So then let me ask you here, why are the boiling points of these three slowly increasing? What is making them different? If you look at this right here, they pretty much have the same intermolecular force. So why is selenium with the two hydrogens slightly higher than the sulfur of the two hydrogens? What is making the boiling point increase as we go down the group? What was the reason again?
You talked about the placement on the periodic table. So S is higher than SE. So S has lower than what SE has, and TE is the highest since it's the lowest on the periodic table.
Right. So the reason there is molar mass. It's heavier. The higher it is in the periodic table, the lighter it is. Remember, the more electrons it has, the electrons enhance the effect. So the electrons enhance the effect of the intermolecular force. So the lower position wise in the periodic table, the more enhanced the effect because of the molar mass. Okay? So I know I've discussed a lot, but you kind of have to see all this. So anyway, I'm moving on now to this one here. One of these compounds is a liquid at room temperature. Which one and why? Okay, so before we even look at the physical state, let's go back and look at this, right? When we talked about the behaviors of solids, liquids, and gases, last week we said gases have little to no intermolecular force. Solids have the highest intermolecular force. What makes this class challenging is you're applying the rule. You're not just memorizing the rule. 1411, many times you were learning the rule. But 1412, you're applying the rule. Same thing with organic chemistry. So 1412 is kind of like a prep class for organic chemistry where you get there, you're applying rules like it's nothing. And everything looks like a puzzle, kind of like what we did with the boiling point. Yeah. So the rule is gases have little to no intermolecular force. Solids have the highest intermolecular force. Now that I have restated the rule, I can reread the question. one of these compounds is a liquid. So one of these compounds has intermediate, right? Because liquid is in between solid and gas. Intermolecular force at room temperature. So when I'm reading questions, I rewrite the question. At first, I was afraid to because I'm like, I can't rewrite the question. I don't know what the author is saying. At some point, I got more confident. I'm like, you know what? I'm going to rewrite the question so it makes more sense to me. One of these compounds is a liquid. Liquid is between solid and gas, right? So they mean intermediate intermolecular force at room temperature. Okay, so let's go through and find out which one has the highest intermolecular force, right? Because that will tell us the state. Which one is the lowest, and then the one that's in between. Okay, they gave us the Lewis structure. Thank you. Okay, which one is the easiest to identify?
The hydrogen peroxide.
Okay, see, you're right there. Look at the number of hydrogen bonds. Yes, that one, that one. Two hydrogen bonds, right? They didn't ask you for that, but you can say it has two hydrogen bonds. If it has a hydrogen bond, what other two intermolecular forces does it have? Dipole, London dispersion force. Okay, now just because it has all three doesn't make it a solid, right? But if it has all three, it has a higher chance of being a solid. If you've bought peroxide from the store, it's usually a liquid, right? But let's go with the rules. Let's not go by real life experience. Okay. Let's see. The other two do not have hydrogen bond, right? Because the F is not attached to an H. The O is not attached to an H. So for sure, these have LDF, and then because you have the third element besides carbon and hydrogen, this is dipole. This one here is dipole. The other way you can look at it is the central atom is surrounded by different elements, right? This is not like the others. Same thing with that one. So we have these two. Okay, so yeah, as far as the intermolecular forces is concerned, this one here has the highest intermolecular force. And then let's see, these two are kind of similar, right? Then they actually gave you the molar masses here, where these, let's see, formaldehyde is the lowest. So based on the intermolecular forces, they go through all this and say, I'm trying to make sure I go through the important parts. Yeah. Since hydrogen peroxide only has, actually, hydrogen peroxide contains two OH bonds, therefore, it has hydrogen bonding. So because this has the highest intermolecular force right here, now I'm realizing they kind of went in a whole different round. The highest intermolecular force, once again, most likely is a solid. It could be a solid or a liquid. Based on the experience we have, hydrogen peroxide is a liquid. So this wasn't the best question to illustrate that point. These two, because they relatively have a lower intermolecular force, these ones here will most likely be gas. They can either be gas or liquid, but comparing the two, because they have a relatively lower intermolecular force, they will most likely be gas. Okay, so bottom line, gases tend to have little or no intermolecular force. Of the two, they tend to have lesser amounts. Solids tend to have the highest intermolecular force. So I would say personally, this question wasn't the best question to illustrate that point. It would have been a lot easier had they used other compounds, right? But the point I was trying to make here is this point right here. Gases have little to no intermolecular forces. Solids have the highest. You won't have questions like this on the exam. The homework maybe, because you do have so many different tries, but I wanted to make sure I made that point so I didn't skip that point, okay? So now we're going to bring in other types of intermolecular force attraction called the ion dipole. In the ion dipole, so before I get into the ion dipole, let me quickly recap, because the ion dipole is now going to metal. So to quickly recap, this is my recap right here. in molecular compounds. Remember molecular compounds from 1411. These are the compounds of the nonmetal and nonmetal, right? In molecular compounds, the three intermolecular forces are, in order, London dispersion force. This is the weakest. Number 2, dipole-dipole. This is the intermediate one. And then finally, we have number 3, hydrogen bond. Okay, this is the strongest. There are other forces out there. So in ionic compounds, intermolecular force of attraction, I'm giving you the short version, is ionic. Okay, so in this case here you have like an ion. And then this is number 2. Number 3, in metallic compounds, intermolecular force is metallic. So I'm trying to keep it simple and not get it too complicated. So if you now are about to discuss ionic dipole, that means that you have an ionic compound combining with a molecule that's polar to get the ion dipole. So we're kind of crisscrossing and comparing different groups or categories of compounds, okay? Understanding that, we're now looking at this. In a mixture, ions from an ionic compound are attracted to the dipole of the polar molecule, meaning that you have an ion from an ionic compound. Okay, easy example here is table salt. And then for the polar compound here is going to be water. Okay, so all these fancy words to say there was some salt that was put in water. But remember, the categories matter. The ionic compound is sodium chloride. The polar compound is water. So does anybody have any questions about that? Why is water being called polar versus the hydrogen bond compound? Does anybody know? Remember, water can hydrogen bond. Of all the bonds it has, that's the most dominant one it has, right? So if the most dominant bond it has, or the most dominant intermolecular force it has, is hydrogen bonding, why is it being called polar? So I'm going to tell you real quick. Water is called polar most of the time, not hydrogen bonding molecule, just because there are more compounds that are polar than there are compounds that can do hydrogen bond. If you look at the structure here, this is showing you an ion dipole interaction, right? This is our water right here, and this is our chlorine. What they're showing you is, even though water has 3 intermolecular forces, water has 3 means to interact with other compounds. It chooses the dipole, the permanent dipole intermolecular force to interact with chlorine. So for you to see that, go back to the Lewis structure for water. Lewis structure for water, oxygen is the more negative, partial negative. Hydrogen is partial positive. Water uses this property here, its polar nature, to interact with chlorine. You can see right here, it is the hydrogen end that's partially positive that is drawn to the chlorine end because opposites attract. Okay, so positive attracts negative. You can't do that with a hydrogen bonding. Same thing over here in table salt, right? Table salt is made up of sodium chloride, so sodium and chlorine. On the sodium side of the table salt, you have oxygen because sodium is positive. Oops, sorry. Because sodium is positive, water uses its negative end to attract the sodium ion. That way we have, again, opposites attract.
How do you determine if they're positive or negative?
In the structure, back to 1411. Let's see. So I have like this mock periodic table that I memorize. So if I don't have one, I'm not panicking. Remember, fluorine is the most electronegative. So I call the elements right before fluorine and fluorine snuff. Oh, I wrote this too close like that. Okay. So we have snuff, right? Fluorine is the most electronegative. And then in the periodic table, hydrogen is somewhere here. So this is like my to-go periodic table in my head. If the element is close to fluorine, then it's more electronegative. So if there's a bond between, let's say, remember hydrogen is so far away from fluorine, so it's the least electronegative. If hydrogen is bonded to carbon, or hydrogen bonded to nitrogen, or hydrogen bonded to oxygen, or hydrogen is bonded to fluorine, the one that's closest to fluorine gets the partial negative sign. So it gets a little bit more complicated than that, but let me start with that, okay? So fluorine gets the partial negative sign because it's more electronegative. By default, hydrogen is partially positive. So partial negative, partial positive, partial negative, partial positive, okay? This one here doesn't follow that rule just because the partial negative and partial positive has to do with electronegativity difference. The difference here, even though in the periodic table they're far from each other, the difference here is not significant enough for any one of these to get the partial negative, partial positive sign. For that reason, CH bond is non-polar. Remember I said last week and today, organic compounds that have only carbon and hydrogen are non-polar? That's why. The difference between these two are not significant enough for them to get that designation. So they only get that sign if they're not sharing these bonds, these electrons here equally. These ones here, they're sharing it equally. Okay, so I know this is 1411. So you're like, oh my goodness, 1411, did that ever happen? Yeah, it happened. It's been a long time ago, but it happened, right? And if you didn't get it clearly in 1411, this is your second chance to learn it because you need to apply it here, right? So what was I saying again? Yeah. So when you're looking at this right here, remember, compared to the two, hydrogen is the partial positive sign, so that's the part that goes to the chlorine. Okay, so the easiest way to recognize this is by ion dipole. Let me see. I have talked about this before. When it comes to interactions, once again, the larger the molar mass, the more electrons. And as you go through the PowerPoint, you realize it's saying the same thing over and over again. The larger the molar electrons, and then they say the larger the electron cloud, increased polarizability. I'll just say more mass, more electrons, and I'll shortcut it here, more effect or greater effect. Whatever intermolecular force you're looking at, it becomes more enhanced when you have more mass. So I'm going to bypass the rest of these words, but ultimately, the greater the molar mass, the greater the effect of the intermolecular force. I bypassed it even more. Okay, that's the bottom line you want to remember, walking away from here. Because chemistry can get very detailed. It is one of those classes where it's like detail galore. They tell you a lot of stuff. And if you're feeling apprehensive, then focus on learning the bottom line. And as you get more comfortable, you feel less nervous about learning the details. Versus shutting down and saying this will never happen. Develop a strategy for dealing with this. If it's like, oh my goodness, this is a lot, start with the bottom line. And most of the time the bottom line have a different color in the PowerPoint, or they have like something like this. This is like a bottom line. Start with that. As you get more comfortable, your mind will react less to the details. Okay, The shape of the molecule matters. The more spread out the molecule, the more interaction it can happen between one molecule and the next, right? The shape matters, the size matters, the type of interaction matters. So, yeah. And so we talked about all of this. I'm not going to go into all of this again. Yeah. So what I want to do right now, I want to summarize what they have written here in context. Actually, I'll just kind of briefly go over it. They're summarizing the intermolecular forces. Actually, I see here the strengths. They have these arranged according to strengths. Remember, with dispersion force, these are the weakest. They're present in all molecules and atoms. The value of the intermolecular forces increases with mass, right? Number 2, polar molecules. You have to decide a molecule is polar before you say it has dipole attractive forces. Remember, if it has dipole, it also has London dispersion force. This is your London dispersion force right here, right? Number 3, if it has hydrogen bonding means it has hydrogen bonding, dipole, and London dispersion force. Hydrogen bonding means it has a OH or NH or FH, right? So I won't even go into all of this. Now, ion dipole is very different. For ion dipole, it just means that it has an ion. So I put here M plus for the ion, and it's attached to a polar molecule. The polar can be water. I'll just write here polar, okay? So you're looking for a metal and the polar molecule, and that would be ion dipole. This one here doesn't follow the trend of the others, but it tends to be of the 4 in the group, it tends to be the strongest, okay? So this is even stronger than the hydrogen bonding. So I'm going to write here, ion dipole is stronger than hydrogen bonding. So they arrange this according to strength. Does anybody have any questions before I move to the application portion? Even more application. Okay. Once again, I'm trying to explain this from the point of view of role versus just information. When I was a student, I struggled with learning things. If it was just information, like, and they weren't connected, I really struggled because I'm like, what's the purpose of all of this, you know? And it's a lot of information. But once it had a purpose, I'm like, okay, I see where this is going. I see how it connects. So remember, we're still learning about intermolecular force. That the whole chapter is about intermolecular force. So now we're looking at vaporization. So apparently, intermolecular force affects forming vapors. Vaporization, that's the forming of vapor. Okay? So what I'm going to do here, they tell you the process here. And so what I want to do is I won't go through the whole process. I'm going to give you guys the bottom line, and we'll see how that bottom line affects this right here. Let's talk about forming a vapor. I'm sorry. My neighbor decided to do a construction right now, so it's like really loud. It's not actually in my apartment. It's apartment next door. Okay. Vaporization essentially is going from, let's see, you're forming a vapor, right? So going from a liquid to a gas, okay? Normally, when you're trying to go from a liquid to a gas, you apply heat. So you heat this up. Okay. As far as intermolecular forces of attractions are concerned, when we are applying heat, okay, so in context of the conversation, when we apply heat, our goal is to break. Yeah, break the intermolecular forces. It's not vindictive, it's science. We're trying to break that bond. That's our goal for applying heat. Whether we're applying heat to melt, whether we are applying heat to boil, we have one goal and one goal only, to break the intermolecular force. Now we can do so once again by boiling. or by melting. Either way, we're applying heat. Okay? Think of, since our goal is to break the intermolecular force, from our point of view, the intermolecular force is like a barrier, right? If we have more to break, we need to apply more heat. Okay. So what was the point I was trying to make? That being the case, if a compound or element has a higher intermolecular force, we have to apply more heat. Okay, my version is just up your game. Bring more heat. They brought more intermolecular forces. You just bring more heat. Then we break all their bonds. Okay. Okay. So once again, this chapter is all about intermolecular force. So when in doubt, intermolecular force, right? So once again, most of these questions will boil down to that. Pun intended. The pun was not intended. Okay. So let's go back to heat of vaporization. We haven't really defined that. So heat of vaporization in chemistry, this is a thermodynamic term. That just means the amount of heat required to vaporize a specific amount of liquid. Okay? So heat of vaporization, like it says in the title, is just the amount of heat required to vaporize a specific amount of liquid. So if I have alcohol here, let me give you the chemical formula of alcohol. I have methanol. So this is methanol. Okay. I'm going to have to add a page. I think that would distort what I wrote. If I have methanol here, versus acetone. I don't know what I'm doing, but I'm doing some science at home. Acetone. Ooh, now I can't spell. Acetone. Okay, nail polish remover. That looks like this. So I have methanol, which is the alcohol. It's not a drinking alcohol. It's the other one that we do not drink. Okay. So I have acetone, and then I have alcohol, the methanol. Which one do you think? So the question here is, which has a higher heat of vaporization? Or let me ask this differently. Which forms, actually, let me change this question from higher to lower. Which forms of vapor easily at room temp? Okay, so the first one is alcohol, the second one is acetone. So here are my structures. Let's start with the first one. Remember, this chapter is all about intermolecular force. So if you have any doubt, draw your Lewis structure, get your intermolecular forces, and then maybe you can kind of ask yourself when you're done, how does the intermolecular force relate to the question, right? So I got my Lewis structure done. What intermolecular forces do I have in this first one? Hello?
You have hydrogen bonding, so you have dipole,
And
LDF.
dispersion? LDF. Yeah, okay. So we got all three, right? Second one. What do we have?
Dipole, and London.
Yeah. LDF, yeah. Okay. At least we got that part down, right? We got our Lewis structure, check. We got our 3 intermolecular forces here. We got it 2 here. So we know with these 3 here, the bonds between the atoms are stronger. Okay. So with that being the case, the heat required to vaporize. If you want to make alcohol a vapor, or if you want to make acetone a vapor, it says here which has lower heat of vaporization. Which one has lower heat of vaporization? Which one do you think will have a lower heat of vaporization?
The
Of the two?
acetone.
Yeah, yeah. Lower heat to vaporize, because all you have to do is overcome 2 bonds, okay? That being the case, yeah, 2 intermolecular forces. That means acetone will easily form vapor at room temperature because the room temperature only has to overcome 2 bonds to make this a gas. It doesn't have to overcome that much, versus this one here has that secret weapon, hydrogen bonding. So most likely, I mean, you will still smell the alcohol. You will, because alcohol is still organic, and organic compounds tend to have a lower boiling point, period. But not like acetone. Nail polish remover is strong. If you don't get your nails done, that's okay. But when you're walking in the mall or Walmart, when the ones that have the nail polish place, whatever, you can smell that from a mile away. You're like, man, those chemicals are strong. The chemicals you're smelling, acetone. Okay? Because the heat of vaporization is very low. They gotta get the nails done, get the nail polish removed. So that's why, yeah. But that's not what we're learning this. That's just where it's applied, right? Okay, very good. You've seen the correlation here, right? So bottom line, when it comes to temperature, lower heat of vaporization has to do with lower intermolecular forces. Okay? So if you have that, it says right here, the rate of vaporization increases, which just means that you have more vapor formed. Okay? The standard, the challenge you're trying to overcome is lower. So lower intermolecular forces, lower heat of vaporization, and then you have more vapor easily formed. Any questions about this? Okay. So actually, as I'm looking at this, I'm trying to focus on the most important thing here. So I won't really go over, because I'm focusing more on you being able to answer the questions, because they do have the slides here somewhat get a little bit wordy. So I think we're good on that when we're talking about heat of vaporization here. Yeah, they give you a more specific definition, the amount of heat required to vaporize 1 mole of liquid. So we've discussed that part. Okay, let's look at our example right here. Heats of vaporization of several liquids at their boiling points and at 25 degrees Celsius. We'll just look at 1. We got water, we got alcohol, we got acetone. So you see they bring them all back, and you got diethyl ether. So with this one here, even though we have the chemical formulas, it helps if you have the Lewis, because the Lewis structure shows you everything. So you got water. So I'll draw water right here. Water. You got rubbing alcohol, isopropyl. This is a stuff that became unavailable for like a lot of months, but now it's back in store. Rubbing alcohol. So this one here is OH. It's got a C. Then I'll write like this, CH3, CH3, and then H. Yeah, like that. Isopropyl alcohol, acetone, CH3, C, double bond O, CH3. Okay, this is acetone. And then diethyl ether, I'm probably going to need more space here. So actually, since I have more space, let me write everything down here.
You're only can you go back to that equation out there, that molecule, the Lewis structure? Why is
Which
it
one?
right here? The CH3, C, CH3, and O.
Wait, hold on a second. I'm trying to write these properly. So it's C. The isopropyl is like this, and they don't necessarily have the structural formula here. So if you're reading a table like this in your homework and you're missing the structural formula, if you know how to draw it, draw it. If you don't know how to draw it, you can look online. Okay? Because knowing the structural formula is important. Jacob, give me just a second. Oh no, why won't it write? Okay, there. CH3. This is isopropyl alcohol. What was your question? And this is acetone right here. Acetone, and I have one more. I have diethyl ether. So diethyl ether is CH3. I have to remember my organic. I haven't taught organic in a long time, so as time is going by, I'm forgetting my basic stuff.
Yeah,
You don't use
the numbers don't add up. Like that's what's confusing me because you got CH3 8 uh H8, but I don't see any H8s there or anything close to it. H4s, H4s.
Oh wait, you're looking about these numbers here?
Yes.
Okay, that one. Okay, C3, right? C3 right here.
Yes.
Oh, sorry, my pencil is struggling. C3. Oh, there. C3, 1, 2, 3, right? H8, 3 plus 3 plus 2 is 8.
Okay.
So this is C3H8O. Okay? This next one here is C3H6O. So it's C3, 3 carbons,
Okay,
H6.
that's it.
You
That's
thought it was H8 again?
yeah. I saw. Thank you.
Yeah. I wasn't really even focused on that because oh, this is diethyl. So my bad. Based on what you actually, this is not dimethyl. It's diethyl. So I have to have CH2, CH2, and then CH3 here. Thank you. So yeah, this is diethyl, and then ether. Okay. Okay, so having said this, so once again, bottom line, we have hydrogen bonding here. You can see that, right? Dipole, dipole, LDF. We have two hydrogen bonding. I'll put that there so you guys can see that. Here we have, in this structure, we have one hydrogen bond. We have dipole, dipole, and then LDF. Over here, there's no hydrogen bond, just dipole, dipole, and LDF. Here, same thing, dipole, dipole, LDF. So you can tell all these four. You guys didn't kind of took water for granted. Is holding its own. So all these four here, essentially, water has the highest boiling point. When it comes to vaporizing water at room temperature, it takes a lot of energy. So it has the highest vaporization temperature. So it takes a lot of energy to vaporize water. So if you're trying to count and compare, you will see some vapor for water, but there will be less vapor for water at room temperature because it takes a lot of heat to make water vapor. So at room temperature, based on this table here, there will be less vapor for water because the room will have to kind of heat up quite a bit to make that vapor. Okay? And then here for rubbing alcohol, the temperature is actually higher. So you have even less vapor. So interestingly enough, because the mass of this compound is higher in this context here, the mass makes rubbing alcohol have even less vapor. Okay? The one that will have the lowest temperature of vaporization in this context here, more than acetone, is actually diethyl ether. You can see based on this table, I'm just going by the table. For that reason, of the four, this will have the most vapor at room temperature.
So the
Okay.
strongest the smell is the strongest, the most vapor, right?
Well, there is the smell and then there's the amount of chemicals. So sometimes we relate it to the strongest smell. So diethyl ether stinks. Oh my goodness. It's worse than acetone. So it just so happens in this case where, yeah, you will smell this and you'll be like, oh my goodness, that's ether. And then acetone smells too, but it's more acceptable. It here it's a coincidence that the one that has the lowest temperature has the worst smell, but sometimes because the smell is based on the chemical, right? Sometimes that's not the case. Sometimes it has a lower temperature and it has a pleasant smell, but you still smell it. Like perfume, perfume will have a low vapor pressure at room temperature because when you spray it, you smell it everywhere, but it's a pleasant smell, right? And we like it, at least most perfumes. The oil-based perfumes, they will have a much lower vaporization temperature, so you will smell those more, right? I was recently trying to buy some oil-based perfume during Christmas, and it's like, yeah, this is stronger. I'm like, yeah, I know because it has a lower temperature vaporization. Huh? Don't worry about it. I know. You don't communicate at that level to people. That's how you get left behind from parties and stuff. Okay, now we're going to be doing some math. It's saying using the heat of vaporization. Okay, hold on. I may have to change the tip on my pencil. It's kind of okay. Give me just a second. I don't know why it's kind of going in and out. Hold on. I don't even know where I put the box. This pencil can be a good thing. It can be a bad thing. Um, Give me just a moment. I mean, I think it's working. I don't think the bad. Okay, there. Stupid pencil. No, it's actually like this pencil. Okay. So using the heat of vaporization in calculation, calculate the mass of water in grams. So what is wanted here is grams of water, right, based on the question, that can be vaporized at its boiling point with 155 kilojoules of heat. So something about boiling point of water, which is 100 degrees Celsius, right? Then I'm being given the amount of heat, Q, which is 155 kilojoules of heat. So they want us to figure out the amount of water that can be boiled at this temperature. So the plan here is we need to actually have this conversion factor, which is the heat of vaporization of water. So this question here, you really can't work on it because I was looking at this question saying, I need a conversion factor. How do I go from kilojoules to degrees Celsius? There's a conversion factor missing. So this table here was to explain something, but to also provide you with this. Look at this information here as a possible conversion factor. Okay. So from the information here, I will use 40.7 as the heat of vaporization of water. So I need that because I'm looking at the units, they don't really mesh. Delta H of vaporization, heat of vaporization of water is 40.7 kilojoules, right? And this is per mole. Now this is beginning to make more sense. So I have degrees Celsius, I have kilojoules. So we'll go from the kilojoules provided. We'll use the conversion factor given to us, and that will give us moles of water. For moles of water, we are one conversion away to getting the mass of water. Now they set it up over here, right? So even though I know they haven't worked it out here, I will work it out here so y'all can see from scratch. So in my conversion here, I have this here, but I don't necessarily need this here. Remember, in our conversion, we have to get to grams of water. So we start with a given number, this number here, because this number does match our conversion, right? So I write my 155 kilojoules, like we did it in 1411, dimension analysis. You draw your brackets, conversion brackets. Remember, whatever number you have here, that unit has to match diagonally down here, right? So down here, whatever number I write, I have to have a unit kilojoules. So I've used the first number, start with a simpler number, and then I look for something else that also has kilojoules in it. Oh, look, right there, my conversion factor, right? Now my conversion factor has to go here. I like to write this number here as a full fraction with a number. So I'll put the 1 down here. It doesn't change the number. Everything is okay. So I'll write the number here. 40.7 kilojoules goes on the bottom because remember, the units have to match diagonally across. 40.7 goes with kilojoules. Then by default, the bottom part of this fraction, 1 mole, goes on top. Okay? So I've used this conversion factor, I've used that number. I still have to get to grams of water. Can I make this a little smaller because I was writing so big like I had forever to write? Okay, right here. Okay, so these are all of water. I should have written that part. Oh, I'm getting lazy. This is not good. Okay, right here, of water. Okay, I have to do one more conversion to get to grams of water. I remember 1 mole of water is the same as 18 grams of water, right? The molar mass of water, all the masses in the periodic table are masses of 1 mole, right? This quality right here that happens sometimes, okay? 1 mole of water, because the mole and the mole has to match, right? Kilojoules, kilojoules match, goes with 18 grams of water. Oh, I have the unit I wanted. My desired unit is right here, so I can stop. I don't have to continue my conversions. Now let's see. Mathematically, 155 times 18 divided by 40.7. What unit does not cancel out? Grams of H2O. So I do my math with my calculator. 155 times 18 divided by 40.7. This is 68.6 grams of water. Oh, I forgot to mention, this is 3 significant figures, right? So your answer will be 3 significant figures from 1411. Okay. Yeah, I know. They're drilling a lot of holes in the wall. So you see the answer they have right here. So man, I didn't get done with the chapter. That's okay. Let me go ahead and go over vapor pressure. That will actually, I'm skipping over all the details that goes into a lot of details, right? I want to talk about vapor pressure right now, and then that will allow us to actually make some advancements in the slide. Yeah. So let me go over vapor pressure. For vapor pressure here, I want to define pressure based on what we covered in 1411. So in 1411, we covered pressure, and we said that pressure is generated when gas molecules collide with the wall of the container. So all you need here is gas molecules, and they have to be colliding, so they have to be made. But we learned this in a different chapter. So how does it apply to this chapter? Well, chemists are a little bit anal when it comes to words. It's like, okay, well, pressure is generated. Oh, I said generated, not generation. When gas molecules collide with the wall of the container, and then they'll be like, well, that was for gases. So when it comes to vapor pressure, we're bringing the term vapor pressure to refer to from liquid, right? This is a gas, but it came from a liquid versus in 1411, the gas was always a gas. To me, I'm like tomato, tomato, right? Vapor pressure is generated when vapor molecules collide with the walls of the container. Okay? It's just, once again, in this context here, this is a vapor that came from a liquid versus 1411, it was always a gas. Okay, so that being the case, back to intermolecular forces, because this whole chapter is talking about how intermolecular force is around our lives this whole time, and we didn't even realize it. The pressure exerted by a vapor when it's in a dynamic equilibrium with its liquid is called a vapor pressure. I gave you the paraphrase version of it. The weaker the attractive forces between the molecules, the more molecules will be in the vapor phase. Therefore, the weaker the attractive forces, the higher the vapor pressure. The higher the vapor pressure, the more volatile the liquid. Okay, what did I just read? Back to intermolecular forces. So now we're talking about gases, but we're discussing gases on top of a liquid. So we have a liquid here, liquid. And the idea is above every liquid, there is a vapor. Every liquid, there is a vapor. Okay? And there is a constant equilibrium between the vapor, the gas from the liquid, and then the molecules in the liquid state. Some of the gases are falling back into the liquid as they lose energy. Remember, gas molecules have high energy. They're moving around constantly colliding with each other. Liquid molecules are moving a lot slower. They're more chill, more laid back. They're held in liquid state by intermolecular forces. But occasionally you have that one liquid that gains its freedom, boop, and bumps or jumps out of the liquid and forms a vapor. But for it to do that, it has to gain so much energy and break free from the bonds that held it. Occasionally, you have a lax vapor molecule that's moving around slowly, and then it gets sucked back into the liquid. So both directions are happening, right? Liquid forming vapor and vapor forming liquid. Slow moving vapor falling back in liquid. High moving liquid getting out of the liquid phase, okay? That equilibrium happens. The question is, how much vapor do you have? And we're being told here, if the intermolecular force in the liquid is high, right? Less vapor forms. Okay? Remember, view gas molecules like free molecules, okay? They're free, they're moving around, they're not being encumbered or held back by intermolecular forces. So if the intermolecular force in the liquid is high, that means fewer molecules can escape to form a gas. And gas molecules are technically just escaped liquid molecules. Okay? So look at these as escaped. They're not prisoners, not really, but escaped liquid molecules. So if the intermolecular force is high, then it's harder for the molecules to escape, right? So having understood this, let's compare two scenarios. One scenario where you have H2O liquid, and then here we're going to have gas. In another scenario, we have, let's go with acetone right here. Acetone liquid and acetone gas. Okay, so I have my water molecules here in a liquid phase, right? How many circles of gas should I draw in the gas phase of water? Should I draw many, considering water is water, or should I draw less? What do y'all think? I know I've skipped a point, right? I did it on purpose. But how about we take a step back since I haven't gotten an answer yet? What is the intermolecular force in water? We've done it so many times by now, right? But let's say it real quick. What is it? Hydrogen bond, dipole, LDF, right? That means the molecules of water, they want to escape. They can't just freely leave. So a few brave ones are able to escape. So I'm going to draw a couple here. Two. Just to say those two made it. But at any point, they can fall back in the liquid, right? But you have a few vapor molecules of water and they escaped. What about acetone? Does anybody remember the intermolecular force? We know the one it didn't have, right? It didn't have hydrogen bond. It had dipole, and it had LDF. So above the liquid state of acetone, do I draw many or fewer gas molecules than water? What do y'all think? Higher or lower? Fewer or many? More or less? This is my last thing because I feel like y'all, it's time to eat, right? Any predictions? What do y'all think? More or less? Is it easier for an acetone molecule to flee? Yeah, it's gonna be more. Man, the standard is so low here. It's like any molecule can be out here. That's why we smell it. When it leaves the container and it gets to our nose, this is our nose right here. Oh, it is good. We smell it. We're like, oh, that's acetone. We can barely even tell there's water around, right? This is many molecules. Acetone easily vaporizes. Gasoline, same thing. When you're pumping gas, when I'm pumping gas and I can smell it, I'm like, oh. On a hot day, when I was younger, I won't tell you when, I used to hate going to the gas station during the day. Because when it's hot in the afternoon, with gasoline having such a low vaporization temperature, right? This is me over analyzing life. Most of the gas I was pumping was evaporating. I could smell it. And I'm like, it's like my money, my dollars just, going into the air. I'm like, come back. But on a cold winter day, I'm like, I could barely smell the gasoline. I'm like, yes, it's still in liquid state. Good. Get into the car. Right. Y'all haven't analyzed things like that? Good for you. People tell me I overthink things. I'm like, okay, whatever. It's chemistry. It's chemistry. But yeah, bottom line is when you have a higher intermolecular force, it makes it harder for the gas molecules to escape because they're being held back, right? Here you have a lower intermolecular force, so many of them escape. So when we meet next on Wednesday, I will talk about the boiling point temperature because I feel like, yeah. And then we'll go into the next chapter. The phase diagram here in this class, yeah, the phase diagram, which is towards the end of this chapter here, should not be that bad. Yeah, this part here, it won't be that bad for us to go through. Wow, we do have a lot to cover. That's why I'm trying to go through the major topics versus go through everything. But we'll be able to go through the phase diagram and finish that part on on Thursday. And then after that, we'll go into the rest of this. Does anybody have any question?
Yes, will you be available for tutoring hours?
Actually,
questions
sorry.
Over homework?
Yes, actually, before I talk about this, I just thought about it. As I looked through the slides, I was like, I don't see us getting all of this done. I feel like we'll complete all of this on Thursday. Does anybody have any time tomorrow after 11:30?
Yes.
Can I at least have 2 people? Because I would like to at least have maybe an hour and a half more, and then the rest of you can watch it in the recording. I apologize. It's just I want you guys to be able to answer questions and ask questions, but I'm looking at the slides left and I'm like, yeah, we won't be able to, if I keep the pace I'm using right now, we won't be able to get to the next chapter Thursday. And I want us to be done with the next chapter Thursday so we can start moving on to, yeah, so we don't fall behind. So if we can meet tomorrow at 11:30, I have to set up a session. If not, yeah, at 11:30. And then for us to make, so it will be just for makeup, for us to continue this. Then I'll record it for those of you who can't show up. Just like today, I'll send a reminder, hey, I'm here. Because I do have a morning 1411 class. And so right after that, I take a 30-minute break. And then, at 11:30 tomorrow, so same time like today. If you can't log in, no problem. All of this is not mandatory, but it does help me record this session and then make it available. So to answer your question, Jacob, were you able to answer the homework question?
Yeah, I got pretty far into it.
Okay. The one with the I2Br2Cl2, you got that one?
Is that the formula one?
That's the one you emailed me.
I think so. I gotta look back over it. I had a couple questions reading whenever I was reading through it, so I just
Uh-huh.
asked you random questions.
Okay. So since he asked me this question, I want to go ahead and address it since he asked. Okay. I think it was talking about boiling points. I'm just going by memory. The boiling point. Ooh, okay, yo, I'm sorry. Spelling boiling point. I think the question was which has the highest boiling point. So we're asking about highest. I'm paraphrasing because I'm not seeing the question right here. And it was comparing I2, BR2, CL2, right? Which has the highest boiling point? I guess that was the question. So you want to go through as usual and draw the Lewis structure. Now, this is going back to 1411. So Lewis, 1411, I, dot, 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 BR. So I'm just paraphrasing this one here. The question and trying to solve it. CL, dot, 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 dot. Okay. So when you look at these, because these molecules look like twin molecules, right? So these all tend to be non-polar. Non-polar. You have a plane of symmetry. You have twin molecules, a plane of symmetry here. So that's another way of quickly telling it's non-polar. There's no difference. All these three are nonpolar. Because all three are nonpolar, the only intermolecular force they have is LDF only. LDF only. LDF only. Okay? So when it comes to the intermolecular force, you can't tell just by looking at it which one has the highest boiling point because they all have LDF. They're all nonpolar. So it's got to be something else. So it wasn't the intermolecular force. The next obvious difference is the molar mass. So you can just say the mass. Okay, I don't have the periodic table right here. I probably should have this memorized, but I don't have the individual masses. I think bromine is around 81 point something, iodine like 127, chlorine 34.5, something in that neighborhood. So chlorine, Cl2 is approximately 70, it's 34.5, so 70, 34.5 times 2. So around, really? Approximately 70, right? Degrees Celsius. Sorry, the mass, so wrong units, grams. And then next, chlorine, bromine, iodine. Bromine is approximately 81, so 81 times 2 is 162 grams. Then iodine is like 127 times 2-ish. I'm just guessing. It's in the neighborhood 254 grams. So obviously the masses are different, right? So from here, you can tell this will have the highest boiling point because it has the greatest molar mass. They probably didn't ask you to write all those words, but that's how you select your answer, and that will be your defense. Okay. Do you have the homework question right now, Jacob?
I have to look at it. Do you have any tutoring hours for that, or?
Can we go over the question right now?
Yeah, I have to look at the questions because I can't go over it right now because I don't have it open.
Okay, as far as let's see. What am I doing? Oh, let me minimize this and see if I can go to the homework. It's harder to answer the question in email, you know? Because I write words and then I'm like, I'm not sure if you got what I'm saying. I'm trying
Yeah,
to describe what
you
they
don't do
want.
you don't do like separate
I do.
group like, hey, we did before where If we have more questions and we still didn't get it, you could collaborate with us.
Yeah, tutoring hours. I can do that. I just wanted to answer you right now, but we can do that later at 2. What time is it right now? It's 1. You want to come back at 2? You want to do it at 3 today?
I do it at 3, so I can be
Okay. Okay. We can do it at 3 then. So at 3, if I forget, just shoot me an email because I usually I get my email on my phone, so that way I can see it at once, just in case I forget, because I could be eating somewhere. You never know. Okay, the rest of you, if you want to join, feel free to join. I will record the session that I have with him later on so that you can have access to it and it'll be posted. If you want to join, go ahead. If you can't, totally understand, right? Because you got things to do. But yeah, so at 3 today, Jacob and I will meet. The rest of you are welcome. If not, I'll just record the session, right? Keep working on your homework. Try to get ahead, and that way, if you do have any questions, you can ask me. So I usually try to keep my office hours between 2 and 4, but I'm somewhat flexible. Sometimes I have meetings I don't even know about, and it pops up. But yeah, overall, just send me an email, and I'll let you know. Okay? Y'all have a nice day. Eat food. I feel like food is calling my name right now. Okay, I'll see you guys. Oh yeah, tomorrow. If not tomorrow, then Thursday. So Thursday we'll pick up where we left off tomorrow. Okay. So I will post the video after our session tomorrow. I need to write myself notes. Y'all don't know how forgetful I am. When I walk away from here, you will
Thursday.
remind me.
Thursday will be where we start.
Yeah. So wherever we get tomorrow, we'll continue on Thursday because the goal tomorrow is for us to catch up, right? So then after we're done with that, so if you can't make it tomorrow morning, watch the video to get caught up, and then when you come in Thursday, we continue. Right. So tomorrow I have an 11:30 session with Chem 1412. Okay, and I'll call that collaborate. I hope it doesn't delete. It's been deleting my stuff. I'll call it a makeup session, and that's Wednesday. So if we need to, Wednesday will be our makeup day, okay? Makeup session. And then today, this afternoon at 3 o'clock, I'll be back here again, 3 p.m. today with Jacob to answer his 1 million questions. Okay.
Hey, it's
Any
gonna
other questions?
help out the whole class.
You what?
It's gonna help out the whole class. I don't know what you're talking.
I guess, whatever you say. Mm. Y'all don't worry. When I was in school, I was Jacob. I was actually worse than him. So, yeah.
Hey, but when I
Okay.
get it, that's it. That's how I understand
Right,
it.
right. You gotta do what you gotta do. Yeah, I get it. I get it. No, I was Jacob, and then you just look at me like, "Are you kidding me?" I'm like, "No, I'm not. I'm not. Do I look like I'm laughing?" Anyway, my teachers still like me, so we're good. Okay, Jacob. See you at 3. The rest of you, feel free to join in whenever. Okay.
Okay, thank you. Thank you.
Okay. You're welcome. Bye.